Alright, in this video, we'll be looking at Graham's law of effusion. That is, Graham's law of effusion. So before we get into Graham's law, what exactly is effusion? Well, this can be best demonstrated with just a simple diagram. So let's say that we have a box. We have a box that is filled with gas. This box is filled with gas, and this box also, it has a hole. And basically what effusion is, so this is filled with gas. And so what effusion is basically the process of this gas escaping the box through this hole. So this gas is going to be effusing through the hole in the box. So that is the process of effusion. And so Graham's law is basically going to be establishing a relationship between the rate of this effusion and the mass, specifically the molar mass of the gases that are effusing. And so again, in chemistry, this effusion process is the process where gas molecules are escaping from some container through a hole or opening, and our Graham's law is basically going to be the relationship between the rate of this effusion and the mass of the gas particles. And kind of boiling it down, the basic underlying principle is that as the molar mass of the gas increases, the rate of its effusion, is going to decrease. So basically, this makes sense, right? Heavier particles are going to move at a slower rate. They're going to be moving slower. And so as the molar mass of molecules involved, if you have as the molar mass of the gases is decreasing, right? If we have lighter gases, the rate at which they effuse is going to be higher. And so this is the basic principle that Graham's law is based on. So now, let's just write out the actual formula for Graham's law of effusion. So, Graham's law of effusion states that the rate of the first gas, let's call it rate 1, divided by the rate of effusion of the second gas is going to be equal to the square root of m2 over m1. That is the molar mass of the second gas over the molar mass of the first gas. And so that is an important distinction, or an important thing to notice, is this sort of inversion of the fractions. And on the left, we're dealing with the rate of the first gas in the numerator, and the denominator is the rate of the second gas, whereas these are flipped. We're looking at the molar mass on the numerator for the second gas, and the denominator is the molar mass of the first gas. And this is, again, comes to be very important when you are just plugging in your values. So make sure that you are keeping this distinction in mind. So now that we have Graham's law sort of, explained or out of the way, let's look at a couple of problems to help it make a bit more sense. All right, so let's say a sample of helium gas effuses at a certain rate. Find the relative rate of effusion of neon gas compared to helium. All right, well, first let's start off by just writing out our Graham's law of effusion, right? The formula is rate 1 over rate 2 is equal to the square root of the molar mass of the second gas over the first gas. So this here is our formula. But let's just make some minor modifications here, right? Instead of calling it gas 1 and gas 2, molar mass 2 and molar mass 1, let us just plug in exactly what we're dealing with in this problem. Let's, in this case, call neon gas 1. Let's say this is rate of neon. And let's call this rate of helium. Divided by molar mass of helium, remember this is inverted now, over molar mass of neon. So this is what we're going to be dealing with here. And so now we're told that a sample of of helium gas is effusing at a certain rate. We're not given the rate, and we're not given the rate of effusion of neon either. We're just told to compare them relatively. So we're not dealing with any real tangible rates here exactly, right? So what do? Well, we just have to use our molar masses because we do have access to molar masses just from our periodic table. So we can write this again to be the rate for neon divided by the rate for helium is going to be equal to the square root of the molar mass of helium, which according to the periodic table is approximately 4, divided by the molar mass of neon, which is approximately 20. This is going to be equal to the square root of 0.2, which again is approximately 0.447. And so we're saying that the rate of neon's effusion divided by the rate of effusion of helium is 0.447. And the problem is asking us the relative rate of effusion of neon gas. And so that really is this answer right here. 0.447 is the relative rate of effusion. We can write this kind of as a percentage too, right? Neon effuses at a rate that is 44.7% that of helium. Or in other words, neon effuses 44.7% slower than helium does. And this makes sense, right? Just based on the theory behind Graham's law of effusion, we said as the molar mass increases, the rate is going to decrease. And we see that neon is heavier than helium is. Helium has a molar mass of 4, whereas neon has a molar mass of 20. And so because of that, it's going to be effusing or moving at a rate that is lesser than our helium will be. In this case, specifically, 44.7% lesser than helium will be effusing. All right, looking at this problem, we're told that an unknown gas effuses 3 times slower than hydrogen gas. Find its molar mass. And we're given here the molar mass of hydrogen gas. Okay, so let's just start by writing out our formula, right? Let's start out by writing out our Graham's law formula in this specific context. So let's say that the rate of our unknown gas, let's just call it x, the rate of x divided by the rate of hydrogen gas, H2, is going to be equal to the square root of the molar mass of our hydrogen gas. Remember again, this is just the most common area for an error with students is they forget that these are swapped or they're inverted, where the rate of x is on the numerator and here it's going to be on the denominator. But yeah, so just don't forget to keep that in mind. And the molar mass of x is here. Okay, so this is what we're dealing with, and we need to now find the molar mass of this x. Well, let's plug in what we found, or what we have. So here in this case, again, we're not given a specific rate. We're just told that the unknown gas is 3 times slower than hydrogen gas. So, in other words, if we were to say, let's just write it like this, the rate of x is equal to, and the rate of hydrogen gas. So, if the rate of if the rate of x, of gas x, this unknown gas, was 1, then the rate of hydrogen gas would be 3. We're told it's 3 times slower, or in other words, the rate of hydrogen is 3 times faster than that of hydrogen, than that of the unknown gas, excuse me. And so, if the unknown gas effuses at a rate of 1, let's say, mole per second, then the hydrogen gas would be 3 times faster than that, right? Or 3 moles per second. If this was 2, this would be 6. If this was 3, this would be 9. And you get the point. So just for simplicity purposes, let's just stick with the original 1 and 3. So since we're not given any specific values for the rate, we can use the fact that the unknown gas is 3 times slower and then set up our ratio. Because if you see here again in Graham's law, really what is happening is we're establishing some sort of a ratio here. We're just dividing rate x by rate of hydrogen. And so we can simply do that by dealing with proportions, right? And so we see that our rate of diffusion of hydrogen gas is 3 times faster than that of our unknown gas. So that's simple enough to just set up as 1 over 3. Because if we put any other number, suppose they gave us a specific rate. Let's say that they told us that this unknown gas diffuses at 9 moles per second, and our hydrogen is diffusing at 27 moles per second. And we set up this expression, or this fraction, right? This rate of x over rate of H2. That would still be 9 over 27, which would simplify to 1 over 3 anyway. And so that is why we can just set this up as 1 over 3 from the very beginning, despite not being given any specific values. Because these specific values would, again, simplify to 1/3 anyway. All right. Hopefully I didn't over-explain that. So we have 1/3, or 1 over 3, is equal to the square root. We have our molar mass of hydrogen gas, that is 2, over the molar mass of our unknown gas. And so now what do? We're trying to solve for the molar mass. And so we can start by just squaring both sides in order to get rid of this square root, right? Squaring both sides gives us, let me just clear up some room here. Squaring both sides gives us 1 over 9 is equal to 2 over the molar mass of our unknown. And now, in order to solve for just the molar mass of our unknown gas, this is simply going to be the molar mass of the unknown gas is going to be equal to 2 times 9, which is equal to 18 grams per mole. And this here is going to be our answer. Again, we're simply algebraically manipulating this expression, right? If you just for clarity purposes, again, in case this is a bit confusing, we have this 1/9 over 2 times, or divided by our molar mass of x. We can start by, let's say, we multiply both sides by 9, right? So multiplying both sides by 9 gives us 1 is equal to 2 times 9 over the molar mass of x. Now multiply both sides by the molar mass of x. Gives us molar mass of x times 1 is equal to 2 times 9 over the molar mass of x times the molar mass of x, which just gives us what we have over here, right? The molar mass of x is equal to 2 times 9, or 18 grams per mole. And so there we have successfully found the molar mass of our unknown gas. Hopefully that made some sense. All right, now let's just look at the next problem. All right, looking at the next problem, we see that a sample of xenon gas, and we're given the molar mass there, takes 2.5 minutes to diffuse from a container. How long would the same volume of nitrogen gas take at the same conditions? All right, so you can see in this problem, we're dealing with something that we haven't exactly dealt with yet, which is time. So let's just address that before we get right into the problem. So, as we know with Graham's law, it's talking about that relationship between the rate and the molar mass, right? We know that as the molar mass increases, as we're dealing with heavier particles, the rate is going to be decreasing, right? We know that as the particles get heavier, they move slower, and so that rate is going to be lower. But what about time? Well, if, again, in this exact scenario, we're dealing with heavier particles of gas, so they move slower, and so it would take more time. It would take more time for these particles to effuse, right? Effuse out of that container. Similar deal going on here when we have lighter particles, when that molar mass is decreasing or is lesser. Well then, because they're lighter, they're going to be moving faster, so that rate is going to be greater. They're going to be dealing with a higher rate. We have lighter particles, they move faster, and so it takes them less time to effuse. It takes less time to effuse. So hopefully this relationship is making sense, right? We're dealing with heavier particles. They move slower. When you're moving slower, it'll take you more time. We're dealing with lighter particles. Those are moving faster. If you're moving faster, it takes you less time to effuse from the container. And so it is this relationship, right? This inverse relationship that is really the basis or reason for that inverse sort of deal we got going with the fractions in rates in Graham's law, right? We see that as molar mass is increasing, rate is decreasing. That's exactly why we see this sort of rate 1 over rate 2 is equal to the square root of molar mass 2 over molar mass 1. The reason we sort of have this opposite inverse deal going on is because we do have this inverse relationship. As molar mass increases, as we get heavier particles, the rate decreases. They're going to be going slower. But what about with time? Well, we see with molar mass and time, as we have heavier particles, it's going to take them more time. So this is sort of a direct relationship. There's nothing inverse going on here. As particles are lighter particles are going to take less time. And so we can kind of, well, not kind of, when we're looking at this sort of expression, we see our rate 1 over rate 2 is equal to m2, square root of m2 over m1. Well, we can see that time and molar mass are more direct. There is no inverse going on there. So really, we can just write this out as T2 over T1, or time 2 over time 1. Rate and time are again going to be inverse. Your rate 1 over rate 2 is going to be equal to time 2 over time 1. But looking at just this portion of the equation, well, we can see that our time and or just looking at this relationship that we've established, we can see that time and molar mass are directly correlated in this way. And so let's just use that fact to our advantage and work out this problem, right? So, writing out the general Graham's law in this exact scenario, we see that our rate of nitrogen over the rate of xenon is equal to the square root of the molar mass of xenon. Again, this inverse relationship over the molar mass of nitrogen. But then, looking at time, again, we know that molar mass and time are directly related there. We can say that firstly, let's just show, again, the rate of N2 and the rate of xenon. These are inverse, again, because we know as rate increases, rate is just talking about, think of it like speed. As you're going faster, it'll take you less time. If you're going slower, you have a lower rate, the time it'll take you to get to a certain destination, or the time it takes for these particles to effuse will be lesser. And so, in this case, it again will be inverse. It's going to be set up in this inverse fashion. But when we are looking, finally, at our relationship between molar mass and time that I was just saying earlier, we can see that this is going to be direct. There's no opposite deal going on here. It's just going to be the molar mass of xenon over the molar mass of nitrogen. So this is what we're going to be using here. And this again is a very common source of a mix-up. And that's why this sort of logical relationship that we can see between rate and molar mass and time is important that you internalize, because that way it won't really be so much of a memorization, and more so you understand why the formula is set up the way that it is. And so this is what we will be using for this problem. So, clearing up some space, we can just keep this formula here just so we have it, in our way, so we can still see what we're trying to do. But we are given our time for xenon to be 2.5 minutes, so 2.5, and we're trying to find the time it takes for nitrogen. And this is equal to the square root of the molar mass of xenon, which we're told is 131, divided by the molar mass of nitrogen, which we're told is 28. And so this gives us 2.5 over the time it takes for nitrogen. which is what we're trying to find, divided by the square, or is equal to the square root of 4.08. And which again, the square root of 4.08 is 2.16 approximately. And so that means let's just do it over here. Time for nitrogen, we're just going to have to manipulate this algebraically. And so we can see the time it takes nitrogen gas is going to effuse is just going to be 2.5 divided by 2.16, or 1.16 minutes. These are our units here. And that is going to be our answer. It will take 1.16 minutes for the same volume of nitrogen gas to effuse, again, at the same conditions. So this here is going to be our answer. So hopefully that made some sense. That brings us to the end of this video. So I hope you got some value out of this video. If you did, please show your support by liking, subscribing, and leave in the comments what you would like to see next. And I'll see you guys in the next one.